Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Kaustubh Rajwade with us today. Hello, Kaustubh.
Hey Frank, happy to be here.
Well, I'm happy you're here to talk about your very lovely article, which we will get to very shortly. And it is June 26th, so we're after solstice of June 2025. So it's summer in the Northern Hemisphere. And how are things? First of all, what is your geolocation and how we doing on the summer?
Yeah, so I'm based at the University of Oxford in the United Kingdom,
Cool.
uh, and probably one of those few times of the year in the UK with excellent weather, So summers in Oxford are fantastic. So yeah,
Uh,
great time to be here.
yeah. I've only visited UK like three times, four times or so. And usually we go to Bristol because that's where our publisher is. IOP is in Bristol. And
Okay.
it's always cloudy.
Yeah. And Oxford is really pretty in the summer. So
Very nice.
even though
Beautiful.
the rest of the time is a bit gloomy,
Beautiful.
but
I'll
I'll
have to
take it.
visit. I'll have to visit sometime in the summer.
Yeah, you should absolutely.
Yeah, and I'm in Phoenix, and we are definitely in our summer mode, and so we're hitting somewhere in the vicinity of 40 C or so, 110s or so. So it's
Wow.
it's lovely.
I guess it's more like summer and mild summer, I guess, for you.
That's right. That's right. We just have shades of summer throughout the year. That's all it is. So very cool.
Yeah, I can imagine.
Very cool. And Costa, what do you like to do for research?
Yeah, so I'm basically, a radio astronomer, particularly involved in time domain radio astronomy. So I started off with pulsars, radio emitting
Of
neutron
course.
stars.
Yes.
And then as I kind of progressed, I got interested in, various different bits and pieces of that, so like fast radio bursts and,
Yes. Yes.
magnetars, all like kind of those exotic subclasses of neutron stars. And
Uh-huh.
more recently, I've been doing a lot of research on long period transients. There's this
Oh,
new
very cool.
thing
Yeah.
subclass of sources that have come about a few years back.
Yep.
Yeah, which are still a mystery to the community. So
Indeed.
yeah, that's basically what I work on.
Very cool. Very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. A coherent radio burst from an X-ray neutron star in the Carina Nebula. And Kaustubh, take us away.
All right, thanks, Frank. Yes, so this is basically an article that's reporting a discovery of a coherent radio burst from a neutron star in our galaxy.
Hmm.
Again, it's authored by me, and I just wanted to give a shout out to my co-authors, especially Jun Tian and George Yunus, who helped me with the radio and the X-ray data analysis. And Basically, this was written as part of this Trap collaboration and some of the collaborators
Hmm.
based in Max Planck Institute for Radio Astronomy
Yeah.
in Bonn.
Yep. Very
Um,
nice international collaboration here. Very cool.
indeed. And also makes use of the Meerkat radio telescope, which I will be
Oh, yeah.
talking about in the article. So, yeah,
Okay.
which is a fantastic radio telescope.
Very cool.
Um,
Let's
Yeah,
get
so
into it.
so this all starts with the collaboration that I'm part of, which is the Mere Trap collaboration. So we are a team that was based in University of Manchester. Now people have kind of gone on to different places.
Yep.
What we did was we built this real-time fast transient detector at the Meerkat telescope.
Okay.
So for those of you who don't know, Meerkat is this 64-dish radio interferometer that is based in the Karoo Desert in South Africa.
Cool.
It is basically a precursor to the Square Kilometer Array, which is going to be one of the largest radio telescopes to be built.
Indeed.
So what we do is that while the data are being taken for all kinds of science at Meerkat, we're using the same data stream to look for fast radio transients in real time.
Okay.
So it could be fast radio bursts, it could be single radio pulses from neutron stars in our galaxy. It's the whole sample of
The
various.
whole zoology of it.
Yeah, exactly. And so on, I think it was 3rd of February of 2024,
Okay.
when we were commensally observing on, one of these many observing proposals at Meerkat, when we saw this single radio burst, right? Our pipeline detected this single radio transient.
Okay.
Um, and um, it was exciting because we knew it was from the galaxy.
Oh,
Um,
nice, nice.
and
Okay.
and then we knew that it was probably from a neutron star in the galaxy, but that's what you typically we get such radio pulses from neutron stars in our galaxy. And
Hmm.
that kind of brings me to the various types of neutron stars,
Yep.
because that's going to be pretty relevant for this paper. So neutron stars, they come in different flavors. So we start off with typically the most common way of discovering neutron stars is through their pulsed radio emission, and we call them pulsars. So the majority of them are, seen as radio pulsars in our galaxy. But of course, there are, different, like I said, various flavors, and they're always oddballs out there. Uh, One of them is the one category of neutron stars is called magnetars, which are like these neutron stars, but with much higher magnetic fields than what are typically seen.
Yes.
So typically they have 10 to the 12 Gauss. In magnetars, the idea is that it's 10 to the 14 Gauss. That's a really, really
Large
large
yield. Yes.
magnetic field.
Ah,
Um, then, of course, there are these other type of neutron stars called X-ray dim isolated neutron stars, or X-DINs.
yes.
These are kind of thermally powered, so you see the X-ray emission
Okay.
from the hot surface of the neutron star.
Hmm.
The magnetic fields are not expected to be as high as a magnetar, but still higher compared to the rest of the population.
Right.
And then you also have this other very small category of compact central objects, CCO.
Hmm.
So these are neutron stars that lie in the central regions of supernova remnants. So we know that they're basically neutron stars because they're clearly in the center of a known supernova remnant.
Awesome.
And
Good.
they're young and much hotter than X-DINs.
Yes.
But very interestingly, the measured magnetic fields of CCOs, so far we only have one kind of confirmed detection,
Okay.
but is much lower than what's expected from a neutron star, like a young neutron star. Typically, young neutron stars tend to have very large magnetic fields, and the idea is that as they evolve, they slow down and the fields decay.
Yep.
But for one of the ones we have measured, it's like 10 to the 11 Gauss, which is like an order of magnitude
Wow.
lower than what you would expect
Okay.
for a young neutron star. So that's very interesting. And so this really,
Okay.
the first obvious question that we have is then that how are these different populations related? Like, is there an evolutionary pathway,
Yeah. Where's the HR
between
diagram for
a
these things?
class? Exactly. And or like what's happening here? Like, are they really completely separated in the sense that they just have different formation channels, or like if they're all formed in the same way,
Yeah.
how does one neutron star go from being a magnetar to an X-DIN, or to a C, or start from like being a CCO to a magnetar to an X-DIN to a
Mm.
radio pulsar, or is there no link, or like what's the order?
Yeah.
So that's still a question, right? There's so many unanswered questions here. And so finding common emission traits is very important between these different classes.
I agree.
And I think that's how we got lucky here, I think here in some, in
Serendipitous
some sense,
discoveries are
because
always wonderful, right? Yeah.
it is because like I think the serendipity is such an important aspect of transient astronomy.
Yeah.
And so you have to be lucky, to make, really make big progress in the field. So,
Yes.
so like I said, we discovered this single pulse, right? Single radio pulse. And then because Meerkat is an interferometer,
Yes.
we managed to even localize it to subarc second, precision. And when we looked at the location, we realized that the location of the source is to within an arc second of a known radio quiet X-ray neutron star in the galaxy. Now
Ooh.
that's very
Ooh.
interesting
Yes.
because X-DINs are not known to be radio loud. There
Okay.
have been searches for radio pulsations in X-DINs so far, or even CCOs, but none have really shown any pulsed radio emission to show any kind of connection between the different populations of neutron stars.
Right.
And so that has always been kind of like, a question, and people have tried to pursue it, trying to figure out, like, try to find radio pulsations from these things, or even radio emission, right? It doesn't have to be
Yeah.
pulsed like a
Yeah.
single
Yeah.
burst like we
To be
saw here.
broadband. Yes. Hmm.
Exactly. So that's why this was quite exciting because this source. I think it's called 2xmm 10 so something something. It's a big number that I don't remember.
Yeah, the telephone
Uh,
number. Yeah,
yeah, exactly. And so this source is a known X-ray source, which is believed to be a neutron star. Yeah, there we go. 2xmm 104608.7 minus
I know
594306.
when
I
I
do
can't
not
remember that
expect
either.
people to remember
It
that.
needs a
I
name.
mean, I myself don't remember it, so
You should name
uh,
it. It needs a name.
I agree. Definitely needs a short. I just call it a 2xmm source. It's easy
There you
for when
go. That
I
works.
was writing the paper.
That works.
Um,
2XMM. Okay.
and so this source is thought to be a neutron star based on the X-ray spectrum from it,
Hmm.
even though we don't see X-ray pulsations from it, which are normally seen from X-DINs and CCOs.
Right.
Just based on the X-ray spectrum we get, it's a nice thermal black body spectrum. So based on that, we know that it's a neutron star.
Okay.
There is an 18 millisecond X-ray pulse period candidate
Okay.
based on some previous, but it was never confirmed.
Okay.
Um, but the fact that we see a radio burst from it confirms that A, it's a neutron star,
Yes.
and B,
Yeah.
it's interesting because this neutron star shows properties consistent with an X-DIN, and we're seeing a radio burst from an X-DIN-like source or a CCO-like source. So that was
Tantalizing hint of
very
a
cool.
connection.
Exactly. So we can go to figure one,
Yeah,
which
sure.
basically
Mm,
shows the
The burst.
pulse, Yeah, this is the burst that we saw. So I'll give you a little bit of an explanation of what the figure is showing.
Mhm.
The bottommost panel is showing kind of a 2D plot of frequency versus time. So
Yeah.
that's the frequency at which Meerkat was observing.
Yes.
And you can see time in milliseconds. So you can see it's a pretty short burst, right? It
Mm.
lasts like, only about 50 milliseconds or so.
Thereabouts. Yeah.
Yeah. The middle panel is just showing the intensity. So
Yeah.
the black line is showing the full total intensity, so total
Okay.
power.
Okay.
The red is showing the total linear polarization.
Oh, nice. Okay.
And the blue is showing the total circular polarization.
Yes.
And so it's pretty common for radio pulses from neutron stars to be highly polarized.
Yeah.
You do see a high degree of linear polarization from them. So that's not very surprising.
Mm-hmm.
And the topmost panel is showing the polarization position angle of the linear polarization.
Okay.
And we will come to that later when I talk about, the
Uh,
kind of the implications of all of this.
yes.
Yeah, it shows like that very interesting shape, and I'll come back to that later. But I think what I really want to point out in this figure is the shape of this burst.
Okay.
It is very peculiar in the sense that it is very unusual to see a radio pulse with this kind of a morphology.
Okay.
Because you see that very bright burst at the beginning, very narrow, very spiky, and then you kind of get this little multiple components as you go in
Yeah,
time,
it bounces
forward
around a
in
little
time.
bit. Uh-huh.
Um, and at first we thought that, okay, those other components could just be because there is some kind of scattering,
Yeah.
in the burst.
Mm-hmm.
Because, if there are free electrons between us and the source, the radio waves are going to get scattered because
Yep.
of that,
Yep.
because of the ISM in our galaxy.
Like the
But
reverberation
that,
almost.
but that can be ruled out because if you look at the bottommost panel,
Okay.
uh, you can see that the narrow burst kind of just extends with roughly the same width across the frequency.
Yes, it
And
does.
if there were scattering, you would
Oh,
see that pulse
expected.
become smear out and become wider and wider at lower frequencies.
Yes. Yep.
And so we believe that that's actually the true width of the wave. It's actually intrinsically very narrow, and that the other components are actually different emission components that are kind of
Right.
showing up. And it seems like they're showing up at lower and lower frequencies as we go in time.
Mm-hmm. Very cool.
So it's very peculiar in the sense that, I mean, at least me personally, I've not seen radio bursts like this from neutron stars very often. It's very rare to see something like this. So it doesn't seem like something that you would see from a typical,
Uh,
pulse that you'd see from a rotating radio pulsar.
right.
Who knows? Like that, does
And
that really got me
you
excited.
definitely see dispersion in that as you go on through to two frequencies. So yeah,
Yeah, exactly.
almost.
Yeah. So if we,
Hmm.
so then what we did was we found it. We were excited. We were like, okay, so is there pulsed radio emission from this thing?
Yeah.
Like, do we like is it a periodically emitting thing, or is this like a one-off thing that just happened?
Okay.
And so what we did was we decided to follow up. So we asked for some time at the 64-meter Mariang telescope
Nice.
which is in Australia.
Hmm.
It's a single dish, and we did a 1 hour long observation to look
Nice.
for a period.
Hmm.
And yeah, we didn't find anything. So there
Okay.
was no pulsed radio emission. It just seemed like this was a one-off thing.
Okay.
Um, then the other possibility was this burst like a sporadic event, very similar to the FRB-like event that we saw almost 5 years ago from this galactic magnetar. I'm
Yeah.
sure people remember SGR 1935,
Yes.
which gave out this mega Jansky burst, and it was associated with an X-ray burst as well.
Yes.
So that was very exciting. Then the next obvious thing or question was there any associated high energy emission?
Fair enough. Okay.
Yeah.
Yes. You would expect.
And then so what we did was we looked at so there are these all sky X-ray monitors, constantly looking for these kind of bursts.
Yep.
Like you have Fermi GBM, we have Swift-BAT.
Yep.
And
Yep.
so we just looked at the triggers if there were any. We also did a sub-threshold search for bursts in the Fermi GBM dataset
Okay.
to see if there was anything around this time or even like a few weeks before, a few weeks after.
Yeah.
Because the idea is that
Okay.
if this neutron star was coming into an active state, we might see some activity in high energies beforehand, before we saw the radio burst.
Right. Precursor motion.
Exactly.
Right. It's almost like an
Exactly.
early warning on earthquakes, right? Something shaking up.
Yeah. Yeah, pretty much. But again, intriguingly, we didn't really find anything at high energies, nothing to
Okay.
indicate that there was something weird happening with the source or not.
So a very
So in some sense, it's exciting and also strange.
yeah.
So yeah, and so then the next thing we thought about was okay. So what does this all mean, right? I mean, so we've seen this one burst.
Bang.
There's no real any associated activity in the high energies or anything. Very similar to like magnetars.
That is
Um,
curious.
and so what's the connection here? What does it mean for like connecting all these populations? Like, are we seeing like kind of a missing link source here that is kind of
So this is
transitioning from being an XDIN or like a CCO to
uh-huh.
like becoming a radio pulsar?
Uh-huh.
Uh, so if you just quickly go to figure two,
Yeah. Let's
um,
pop down.
so before I kind of go deeper into like the implications of all of this,
Okay, we got
um,
discovery, and here we go with field images. There we go.
yeah, so I just wanted to show you kind of the localization here, which I think is a kind of a
Pretty
cool
good.
figure. So this, I mean, this just shows you the power of Meerkat in some ways, because these two, starting from the left, the
Hmm.
two images that you see are 300 millisecond radio images from Meerkat. This
Awesome.
is literally take only 300 milliseconds of data, and you can already see the bright radio emission coming from the Carina Nebula, from the star forming region.
That's impressive.
And we were just lucky that this source happens to be in that little gap in the radio emission, so we could actually see it in the images and localize it as the inset shows.
Yeah.
Uh, but this just shows the power of Meerkat, that even at such small integration times, the PSF is so good that you can really make high fidelity images. Like
Hmm.
it's absolutely stunning.
That's what the
Um,
black here. This is a measure of the beam
yeah,
size.
that's the PSF. Yeah, that's how the
Yeah, yeah.
PSF is at with 300 milliseconds of data, which you
Yeah.
can't really say about a lot of radio telescopes, right? I mean, just the UV coverage is really amazing for this
That's
telescope. So,
impressive. Very
yeah.
impressive.
And the rightmost image just shows you the difference image. So if you just subtract out the
Yep.
image when the pulse was
Beam,
there and
beam,
with, yeah,
and
and
bam.
you can obviously
Very
see it
clean.
that kind of sticks out like a sore thumb.
Very clean. Okay.
Yeah. Um, so yeah, and so let's coming back to the implications again, right? So this was very exciting, right? We kind of have this burst. It looks very peculiar, unlike anything that's seen from like typical, radio pulsars. It's a one-off.
Yeah,
So
it's a
again, it
one-offer.
kind of takes
It's a
like
wow
it's
signal.
very, yeah, exactly. So it's kind of comparable to this FRB-like event that we saw from the magnetar.
Yep.
So there are many questions here. First one is that, okay, is this a transitioning source between typical radio pulsars and X-DINs or CCOs? So
Okay.
your CCOs are radio quiet, and the idea is that theory says that eventually their magnetic field kind of amplifies enough as they evolve for it to trigger coherent radio emission mechanism in the
Okay.
magnetosphere. And
Okay.
so is this something similar happening with this source?
Maybe.
Um, so one of the challenges we had was that we couldn't really rule out fully or kind of confirm whether it is an XDIN or a CCO.
Okay.
It could be either based on its X-ray properties. One of the main evidences for it being a CCO is to see if there's a supernova remnant there.
Right.
But this field is so crowded and it's like in the middle of a star forming region. So
Right.
really looking for any signs of supernova remnant is really
Challenging.
very challenging.
Challenging.
I mean, even the JWST images are not going to help us here,
Right.
unfortunately.
Okay.
Uh,
That's a
so that was one of the key things. So we cannot fully confirm that, this is definitely an XDIN or definitely a CCO. But there are definitely, ideas out there like this for the CCO one. And then there's the XDIN angle as well, where there are these ideas that magnetars eventually their fields decay and eventually turn into XDINs.
yes, that's an evolutionary.
So,
Yeah.
so that's also another possibility here, which is kind of shows you again. But I mean, regardless, I think what the main point here is that we have shown that this is a transitioning source. Like we've found like a source that is connecting probably potentially multiple subpopulations of neutron stars,
Yep.
and that was like I think the most kind of the key takeaway
Absolutely. Even
from
if we don't understand it all yet. That's
yeah, exactly,
right.
exactly. Um, and the other idea was that if we assume that this burst was like this FRB-like burst,
Okay.
it makes sense that we didn't see the high energy counterpart because the luminosity. So if we go to figure 3,
Yeah.
I think that explains it really nicely.
Idea.
Um,
Let's see the follow-ups. We talked about that. High energy searches. Ooh, here we go. Nice, nice. Okay.
right. So I think this figure kind of summarizes the result in like this one space. So what I'm showing here is the radial luminosity of these, the radio emission from various populations of neutron stars
Mm-hmm.
as a function of X-ray luminosity,
I'm
right? The thermal, mostly the soft X-ray luminosity, as you can see, it's 0.2 to
yeah,
10
right,
keV.
right. Mm-hmm.
And the various bands are basically showing kind of the typical luminosity range in X-rays for CCOs and X-DINs. Um,
Okay.
and you can see the SGR 1935 burst there, shown in, I guess it's magenta. Yeah.
Yep.
And you can see there are the two bursts, which are like those FRB-like bursts, but there are also some other sporadic bursts, which are closer to the general population, the two diamonds there.
Yeah.
And so you can see that the same neutron star can emit sporadic bursts over a range of luminosities.
Wow. Yes.
Right?
Yeah.
But the high energy emission was only associated with the most luminous radio burst in 1935.
Okay.
So similarly, if we assume the same for 2XMM source as well, it's
Okay.
possible that the reason we didn't see it is that the X-ray luminosity was also quite low and was beyond the detection, the sensitivity of our current instruments.
Right. Okay.
And the other thing I want to point out here is that if you look at the black triangle, which denotes the 2XMM source from this work,
Mm-hmm.
it sits very much in that between where the
Yes.
magnetars
Yes.
are
Yes.
and
Yes.
also where the X-DINs are, which is I really like that about this
Very
plot.
nice.
And so this is kind of showing that, maybe it's kind of straddling the boundary of these two subpopulations. And if that's the case, it's very exciting because it might be this missing link.
Mm-hmm.
But of course, this is only the beginning, and I think we need to do more observations.
We'll come back to that. We'll come back to
Yeah.
that point. Okay.
And then lastly, we basically go into discussing how we can explain this very peculiar radio emission that we see
Okay.
from this source, this neutron star. So if we go to figure 4, I think there's this nice schematic that we kind of a very simple kind of a toy model that we came up with.
Ah, the geometry.
Uh,
Yes. Always.
yeah, yeah.
Always
To kind of
good.
explain, basically, figure four is our idea of how we explain figure one, right? That's how it is. So,
Right.
um,
So it's rotating.
so I'll just give you kind of a quick, quick introduction and description of this.
Yeah.
Um,
Please.
so here's a neutron star, right? You have the dipolar field lines coming out from the along the magnetic axis,
Yep.
and it's rotating kind of, from right to left,
Hmm.
uh, and you can see there's the observer that on the top. So if you imagine in the magnetosphere, there are these different confined regions, that are emitting coherent radio emission,
Yes.
right?
Yes.
And they're moving along the magnetic field line, these
Good enough.
specific, you can call them like, charged bunches or a plasma, right? Like that's
There you go.
confined
Yep.
and that's, accelerating along the lines and it's emitting radio waves.
Hmm.
Um, Now we know from radio pulsars that the frequency of radio observation depends on the height at which the charged bunch that's responsible, or the plasma that's responsible for this emission is from the surface of the neutron star.
I'm with
So
you.
that's exactly what the colors are denoting here.
Hmm. Hmm.
So as
I,
your color is changing, you're basically going to, so if you from light to dark, you're going from higher to lower frequent radio frequencies,
yes.
right? And so imagine you have these kind of confined emission regions, or we call it
Okay.
different, yeah, and the neutron stars rotating. And so as the line of sight is cutting these different regions, they're cutting them at different heights,
Yeah.
which means they are basically seeing them at different radio frequencies. And because they're confined, you're actually seeing different components. So you can imagine you see
Correct.
the first component all the way from the highest frequencies, but the other components are kind of showing up at lower and lower frequencies as time progresses,
Right.
uh,
Right.
as the line of sight kind of cuts through the components. Uh,
Yes. Exactly.
Now, coming back now, this, like I mentioned to you from figure one, we'll come back to the polarization position angle, right? And the shape.
Yes. Yes.
Right?
Let's just
So,
revisit that very shortly here, just to
yeah,
refresh memories. Here's our position angle. There's the burst. Position angle going, yeah, minus 60 up to about 60 and then decays.
exactly.
Okay.
So
Okay.
what's happening is that because the first component is a lower, like it's at a much lower height, the projected kind of the gradient of the change of the PA is much faster at the smaller height. Right?
Correct. Correct.
Because
I'm with
yeah,
you.
exactly.
Mhm.
Because the dipolar field lines are kind of curving up, and so the gradient is kind of becoming much shallower and shallower at higher heights. And
Correct.
so as you're reaching the higher heights, the low
Ah,
frequencies, the gradient is kind of changing. So the rate of change of the
yes.
pH changing. And so you can see it's very steep at the beginning and then it kind of flattens out.
Flattens out as you go.
So that observation is also kind of consistent with this kind of a simple toy model.
Very cool.
So that's the idea here.
Very
Of course, this is not, I mean, this is like I said, it's a phenomenological model. It's a toy model.
sure.
It's not necessarily super accurate, but it's something to start with, something that,
Exactly. Exactly.
yeah,
And from there, you can either confirm this simple picture or you can point out problems with it in the future, but at least it gets us started.
exactly. Yeah, exactly.
Very
And,
cool.
and like the simpler your model is, the better it is because then it gives you some room as
It
well
gives
to
you a
add
warm fuzzy.
some.
You actually understand what's going on.
Yeah, exactly. Yeah, because it's like, when they say that you put in enough free parameters and then you can fit a cow, right? Like that's kind
Yeah,
of the thing.
yeah. Well, that's kind of like why we like analytic formulas so much. We know
Yeah,
they're probably wrong in detail, but they're simple, they're understandable. We get a lot out of it. So
exactly.
I love
Yeah.
this figure. It's beautiful.
Thanks. Yeah, and then I think this really, I mean, leads me to the summary here, really,
Mhm.
which is that, you know, the only point I would like to make is that, yeah, commensal really shows you the power of commensal observing. You want to keep looking
Absolutely.
for transients in real time constantly because you never know what you're going to find. There's always this possibility of, expanding parameter spaces. And this example clearly shows it. Like we were not
Yeah.
expecting anything. We just saw this burst, and then that just led to so much,
Yep.
gave us so much information, really told us so much about evolution of neutron stars. And yeah, I think in the future as well, I think we need to continue really doing real-time commensal searches for fast transients.
Mm,
And this is, I think, only the beginning, and who knows, we might be, finding there will be many more exciting discoveries to come in this field.
very cool. Very cool. And we should mark off that there are some technical details in the appendix here if people want to check them out.
Yeah. So in the appendices, we have gone through some more detail about like how we computed the radioluminosity and like how we did the chance coincidence analysis, because that's
Yes.
quite
Yeah.
important because it's a very crowded field. And
Yes.
so the chance of there being an X-ray source and a different radio source is quite high. But thanks to Meerkat's amazing, precision,
Yeah. Nope.
in like in terms of its localization capabilities and its astrometry, we were easily able to rule that out. But yeah, and also we talk about how we did the searches for a period in the different components of the burst as
Mhm.
well. So
Mhm.
yeah, I would, or encourage people to check it out if they're interested in the details. So
Very good. Give a shout out to a Stingray there while I'm here. Very good. Beautiful. Beautiful. Awesome. Kaustubh, I want to thank you so much for walking us through your very awesome discovery paper. Very nice.
oh no, yeah, I mean, I was very happy to do that. Yeah.
Very cool. All right. And you kind of mentioned it a couple of times there in sort of broad terms. And so let me ask, where do you think we go from here, given the published article? Is there any particular follow-up on this object? Maybe in a variety of methods. And of course, there's always more serendipitous discoveries. And so I'm curious, where do you think we go from here? This is probably not the final article in this, so where do we go?
Yeah, absolutely. Like I already mentioned right in my concluding remarks that this is just the beginning. So,
Mm-hmm.
and so obviously we have already planned follow-up for this particular source, but I think this is just showing that there's a possibility that a lot of this sample of XDINs and CCOs that we know of probably emit such radio bursts,
We just
and we
haven't
have just
found them.
missed them
Yeah,
because we're
we haven't
not
found them.
monitoring them. We're not regularly following them up at radio wavelengths. People have done those searches in the past as like a one-time thing, didn't see anything, and then
Moved on.
I mean, that's expected,
Yeah,
right?
that's what
Telescope
you're gonna do. I
resources are
didn't find
limited,
anything. Move
so
on.
exactly, and telescope resources are limited, so people will move on to other things. So but I think this is really showing us that we need to continue monitoring even the other extents, because who knows, they also might be emitting such interesting sporadic bursts and that we have just missed them so far. Or they are kind of transitioning into becoming pulsed radio emitters and then kind of switch off again and switch on again. Who knows? I mean, the possibilities are endless here.
Yes.
And so I think this really I think this result hopefully, kind of galvanizes the community to do this on a more regular basis. And, who knows, we might find even more. And, finally, we will be able to answer these important questions about the evolution of neutron stars. So,
Tax, pay attention, tax. Give them the time. Give them the time. Very cool. Very nice. Kaustubh, thank you so much for walking us through your very awesome article. Very nice.
yeah, no, thank you so much for having me, Frank.
Yeah, and it'll be really fun to see this field develop over the next couple of years. So, very cool.
Yeah, I hope so too. Yeah, fingers crossed.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.